Alright, this is 9.3, the third lesson in Unit 9, and today we're going to talk about exponential growth and decay. Previous lessons we've talked about using exponents to simplify. Well, now we're going to talk about real-world situations that involve exponential ideas. So your aim is that I can use properties of exponents to analyze real-world situations involving exponential growth and decay. Growth means getting big, and decay means getting small. So let's read right here. There are many things in the real world that grow faster as they grow larger, or decrease slower as they get smaller. These types of phenomena, loosely speaking, are known as exponential growth and decay in the case of decreasing. In today's lesson, we will look at both growth and decay. So exercise 1 is a problem about exponential growth, about a rumor. So the number of people who have heard a rumor often grows exponentially, right? Consider a rumor that starts with 3 people, where the number of people who heard it doubles each day that it's spread. So you guys know how rumors work, right? You tell one person something, then that person tells someone, and you've already told another person. So the rumor starts to spread very, very quickly, right? So letter A says, why does it make sense that a number of people who have heard a rumor would grow exponentially, meaning go faster and spread the rumor faster and faster and faster? Well, the more people, excuse me, the more people who know the rumor, the faster it will spread since more people can tell it. It isn't like if you tell a rumor to one person, you don't tell the rumor again, right? You tell the rumor to, say, your friend, and you're going to tell the rumor to someone else while they're telling the rumor to someone else. So it grows faster and faster. This is just one example of exponential growth. Letter B says, fill in the table below for the number of people, N, who knew the rumor after it has been spread a certain day. So here's how this table works. This table says, look, on the first day, 0 day, 3 people knew the rumor. On the second day, after 1 day, 6 people knew it. On the second day, it doubled again, so 12 people knew it. And on the third day, it doubled again to 24, and it's just going to keep doubling the number before it. So on the 5th day, we've gone from 3 people knowing it to 96 people knowing it. It grew very rapidly, right? As this is going every time, this is doubling, or you can say, you're multiplying by 2 each time, which is different than a linear, where a linear added by something every time. Exponential multiplies by something every time. Okay? So now let's continue with this idea here, with this rumor. In exercise 2, it says we'd like to determine the number of people who know the rumor after 20 days. So if I go back to my table, I could keep filling this out until I get to the number 20, but it would take me a while. So could we think of an equation where I just plug the number 20 in and figure out how many days I would have? So let's develop that, right? So letter A says, for the following number of days, fill in how you calculate your values based on the extended products, using the number 2. So on day 0, there were 3 people. After that, on the second day, after the first day, you multiplied it by 2 to have 6 people, right? So we got 6 here knew it. On the next day, you took the 6, which is 3 times 2, and multiplied it by 2 to get 3 times 2 times 2 to get that 12. Then, it makes sense that the next day, you're going to just take this right here, what you got, and multiply that by 2, right? So, this becomes, in an interesting way, let's write this in a different way. This becomes 3 times 2 squared. Sorry, my pen is being weird. This becomes 3 times 2 squared. Okay? Which gives us that gives us 12. The next day, we're going to take that 3 times 2 squared, and we're going to double that. So we're going to multiply that by 2. This gives us 3 times 2 times 2 times 2, which gives us 3 times 2 cubed now, which gives us the 24. Okay, so you see how I'm taking whatever I get and then I'm multiplying it by this 2 every time? So the next day, I'm going to take this 3 times 2 to the third, and double that, multiply it by 2. Now I'm going to have 3 times 2 times 2 times 2, which is 3 times 2 to the 4th, to give me 48. Do you see how what's happening to this exponent every time? It's going 3 times 2 squared, 3 times 2 to the 3rd. This is the only thing changing in my formula. So it makes sense that my final one, if I have this 3 times 2 to the 4th, my final one should be 3 times 2 to the 5th, which is 96 on your calculator. Okay? So letter B now says, using this pattern we've developed, this pattern of these exponents increasing, write an equation giving the number of people who know the rumor n if you know the number of days. So notice that the number of days, if I can circle this, notice the 2 matches the 2 in the formula. Here the 3 match the 3 in the formula. The 4 match the 4. So in other words, this D is what's changing. So my formula becomes n equals, I'll keep this 3 times 2, but now my variable is going to become the exponent on top of the 2. Okay, 3 times 2 to the D, where if I plug in the number of days and calculate, I will get how many people will know the rumor. So for letter C, I can say, okay, if my formula is n equals 3 times 2 to the days, and I want to know how many people will know the rumor after 20 days, I'm going to plug 20 in for D. Okay, now I know that some of you don't have your calculators at home with you, and that's okay. If you go to Google, like I'm about to do here, and I go on Google, and I can type in calculator into Google right here on my screen, right? Let me make this smaller. And what am I trying to plug in? I'm trying to plug in this 3 times n to the 2. So on my calculator, oh, sorry, I don't know what my thing is doing. On my calculator, I'm going to type in 3 times, then parentheses, 2, and then I'm going to push this button right here, which will pop up a little square, and I can put in 20. When I hit equals, I'm going to get a very big number, which makes sense, because when we're talking exponential functions, oops, this number grows very big. So I get this 3145728, 3145728, which is 3,145,728. So even if you don't have a calculator at home, you can use Google Calculator, and it will let you do these simple calculations. I don't expect you to do this in your head at all. I do expect you to use a calculator, because this is a very big number, 3 million people. But isn't that kind of crazy that after 20 days, 3 million people would know this rumor? That's how exponential functions work. They grow very quickly or they decay very quickly. Okay? So finally, this question, letter D, says exponential growth can be very fast. Obviously, it can go up to 3 million people in 20 days. Assuming our equation from B holds, how many days will it take for the number of people knowing the rumor to surpass the population of the United States, which is approximately 315 million people? So a way to try and solve a problem like this is to guess and check. So I'm going to start with n of 25. Let's try 25 days. When I plug this in, 3 times 2 to the 25 on your calculator, and I can show you if I put this in the calculator, 3 parentheses 2 to the 25 and hit enter, I get 100 million. So I get around 100 million people when I plug that in. Okay, that's too small, right? I want to go over 315. So let's try the next one. Let's try n of 26. 3 times 2 to the 26, and let's go to calculator and see what I get. So I'm going to clear this and do 3 parentheses 2 parentheses to the 26th, and I'm going to hit equals. Now I'm getting closer. Now I've got 201 million. That's still not what I want though, because I want to be over 315, but I'm getting closer. So now let's try n to the 27. So 3 times 2 to the 27. Clear calculator, 3 parentheses 2 to the 27. And there we go. I got 402 million. So on the 27th day, it surpassed the population of the U.S. Okay? So the whole point of this problem was to get you to practice, plugging this into a calculator, to let you understand how the pattern of something exponential can grow very, very quickly, and to get a sense of this equation, this 3 parentheses where this is your variable. The variable is the exponent, okay? Which is kind of a new idea for a lot of us, all right? So let's go on to the next problem. So we've got one more problem on this, and that's going to talk about decay. Now this is a really cool problem, actually. It's a fun problem, I think. So here's the exercise. Helmut from Finland is heading towards a lighthouse in a very peculiar way. He starts 160 feet from the lighthouse. So here's the lighthouse right here. There's the lighthouse, and here's the guy. And he's 160 feet away. On his first trip, he walks half the distance to the lighthouse. So on his first trip, he walks to about here. On his next trip, he walks half of what's left. So here's half of what's left right here, and he walks half of that. On each consecutive trip, he keeps just going half of what's left over, right? So he's just going half and half and half. So we're going to model this distance using an equation and a table to get an idea of how decay works. Okay, so that's the situation. So, exercise letter A says fill in the table for the amount of distance he has after so many trips. So he starts off at 160. After the first trip, he's got 80 feet left. After the second trip, if we're going down by half, so what's half of 80? Half of 80 is 40. On the next trip, what's half of 40? 20. What's half of 20? 10. So we're going down by half each time. So letter B says each entry in the table could be found by multiplying the previous number by what number? This is important because we always want to think about exponential functions in terms of multiplying, not dividing. So don't think of this as taking 160 divided by 2. Instead, think of it as multiplying by a half. So we're really multiplying by 1/2 each time. So example, 160 times 1/2 equals 80. 80 times 1/2 equals 40. So think of it more as multiplication, not division. Okay? Like in exercise number 2A, we want to see this process as repeated multiplication by 1/2. So they're saying, look, let's take a look like exercise this right here where we did this portion. Let's do this now for this new idea where we're trying to find this pattern. So now I'm going to look at this pattern. I started off with, at 0 trips, he started off at 160. After the first day, we multiplied by 1/2 to get 80. On the second day, we multiplied that 80 by 1/2, okay, which 80 times 1/2 is the same thing as saying 160 times 1/2 times 1/2, right? Because we always want to keep that starting value with us. So we can also say it's like saying 160 times 1/2 squared. It's the same thing, right? It would give us 40. Then I'm going to have the same pattern again. I've got this 160 times 1/2 squared, but I'm decreasing it by half again, so I'm going to multiply it by 1/2. This is going to give me another 160, but now instead of it being squared, now it's cubed because I've got 3 1/2s. This will give me 20. So are we starting to see the pattern here? I'm going to put the 160 times 1/2 cubed, but I'm going to multiply it by 1/2 again because he's going to continue to go to half each time. And now this gives me 160 1/2 to the 4th. Notice, what is changing every time? What's the variable? The variable is the exponent, right? The d, 2 and 2, 3 and 3, 4 and 4. So in an exponential of growth and decay, the variable is the exponent. So letter D, based on this pattern, letter C, what could our equation be? Well, D is going to equal the 160 because that stayed the same. The 1/2, which is the multiplier, but now n is becoming that variable, right? That's what changed. That n is what changed. So letter E says, how far is Helmut from the landfill after 6 trips? Well, now we have to plug in 6. So I'm going to plug in 160, 1/2, and now I'm going to plug in 6. So the calculator will do this as well if I plug it into the calculator. So I'm going to close this and open up my calculator again. 160 parentheses 1/2 of 6. So I'm going to have 160 parentheses. I can turn that 1/2 into 0.5, or I could do 1 divided by 2 because that's what 1/2 is. Make my exponent 6 and enter, and I get 2 2.5 feet. So he's 2.5 feet away after 6 trips. So now this brings us to letter F. Helmut believes he'll reach the windmill after 10 trips. Is he correct? Well, let's see. Now we're going to plug in 160 1/2 to the 10th now, right? We're plugging in 10 in for this. So let's go back to my calculator on Google because I don't have my nice one at home. So I'm going to do 160 parentheses 1 divided by 2 parentheses, and now my new exponent will be 10 because he wants to see if we after 10 trips. I hit enter and I get 0.15625. So I get 0.15625. What does this tells me? It tells me that no, he still has 0.15625 feet left. Basically, his toe is right outside the windmill, but is he touching it? No, he's very close, but he's not touching it. So this leads me to tell you why this problem is cool. This is kind of an old mathematical problem that mathematicians talk about a lot. Explain why he'll never reach the windmill. Because if I keep going half every time to someplace, I'm going to show you guys in class what I mean by this. I'm cutting my distance in half every time. I'm never actually going to get there because every time I just cut it in half. So he's always going to have some amount left because he just keeps having it every time. He doesn't actually say, okay, I'm almost there, let's just take that final step. He says, okay, tomorrow I'll go half of what I have left. So he'll always have some amount left because he's taking it in halves. Okay, it's a really neat problem, and I can show you, I can explain more in class, I can show you physically what this looks like. So finally, the last problem of this lesson talks about domain. So domain comes up a lot, and we got to remember what domain means. Remember, domain means the input values, right? And in this case, the input values are the trips. So another way this question is saying why is the trips of this function only whole numbers? Why can't we have 1.5 trips? Well, can you go 1.5 trips? Can you take a trip to the bodega? Can you go 1.5 times to the bodega? No, you either go to the bodega or you don't. You either go twice or you go once, right? So in this case, you cannot, you can't take a fraction or a decimal trips. It doesn't make sense. And Common Core likes to do this. It likes to make sure you're making sense of the problem. So you can only have, 1, 2, 3, 4, 5, etc. trips. You can't have something like, you can't have, 1.8 trips, right? You also can't have negative trips. You can't have -5 trips, right? So when you're thinking about domain, you have to think about what makes sense in the problem. In this case, only whole numbers make sense. So this is a conceptual lesson. It's also the practice of using a calculator and plugging in exponents, and I'll show you guys in class how to do on the yellow calculators. But this is a sense-making lesson. So that's why mastery for 9.3 and 9.4 are together, because 9.4 is more about dealing with the equation and the function and applying a problem like this into an equation. So after you're done with this lesson, please work on the fluency and ask questions. I know this is confusing. So if you don't ask me a question, I'm going to be a little skeptical. Okay? So good luck on your fluency, and remember mastery for 9.3 and 9.4 together.